So for the viewers, just switching in, we just treated a bit of historical motivation, and we're not going to repeat that. You can read it on Wikipedia. It's actually brief. Okay, so let's, with the introduction over, let's talk about the setup. So not all of the variables will be introduced immediately. I'll just write everything down immediately, because then sort of you can look back at it when we do use it. Most of this we've seen before. So we take R and K non-zero natural numbers. We take a matrix, which is a K times R matrix with coefficients in integers. We'll have a vector H with R coordinates, all of them positive, and we'll have x1 up to xn iid random variables. With image in set 1 to R and some distribution P, and we assume that for none of them are constant, and all of the are possibilities are all the possibilities have a non-zero probability. We'll write small letters for the data, maybe sampling from xn. We'll eventually have a theta vector with k positive coefficients, coordinates, and we'll have u in n to the r. This will be a vector of counts, by which I mean that the every jth coordinate equals the number of I such that xi is equal to j. So we have some data, we count how often every option occurs. We will have a t statistic, nice statistics. I forgot to look at what that meant. So at least it needs to satisfy two properties, namely t of v equals 0 if and only if v over n lies in the exponential family determined by that a and that h. I will remind you what that means in a little bit. And we also need that t is increasing away from its zeros. And we'll have v, the random variable, with image in 1 up to r to n, and marginal distribution B. So it's
So
just
Erik, I was still reading something when you wrote the first bullet. Can you explain again what that bullet says, the first bullet over there?
this. Right. So I haven't yet reminded you of what this set is, but I will. And when I do that, is that then enough? Sorry.
What does it mean for functions to be decreasing away from its zero?
I guess what I mean, maybe I mean it's just the function is only 0 there, otherwise it's positive, I guess.
I don't know.
I guess that's what I mean.
Okay.
So just
Like maybe it was-
copy it from the book. It's actually not super relevant, but I mean,
Okay.
yeah, I think we can do everything if we say that T of V is positive. Otherwise,
And so we have lots of, so this, we have x1 of xn, which are ideally probably just a random variable. We
Yes.
also have v. Is this a random variable on the same probability space, or?
yeah, I guess so.
Or is V the vector x1 up to xn?
I think it will always be just a vector x1, 2, so maybe I should. I think that's what we actually do all throughout. So I think it's enough to
Because we have
say that.
we have this sort of convention where like we write random variable and then all the other associated data is implicit, which is fine, except that I find it very confusing to know which random variables have the same implicit
Right,
data.
yes.
So this is next to the question. But
Yes, but I think all throughout it's just sufficient to assume this. So just to recall from previous lectures, what is this set? This is a set of probability distributions satisfying the following. There exists a theta, so as I said, theta will always live there, and a function z such that for all j we have pj is equal to that's this set of probability distributions. And actually, this is the same. We've seen this in Amin's talk. With the underline, I mean this is a vector. I remember this was confusion. If one is an image of A, then we can also write it like that. Okay, and another object that we will need, where I guess I've taken h equal to 1, was this ideal. I've also seen Amin's talk. Which is associated to the kernel of A, and the notation, if you don't remember, is a bit confusing because P has several components, U has several components. So if I write P to the U, I mean P1 to the U1 times P2 to the U2 times P3 to the U3, etc. So this is a monomial in this polynomial ring. So the P is a probability distribution, but we will treat its components as variables in a polynomial ring. And actually that will be very useful.
Sorry, Erik.
Yes.
Your first definition of this MAH,
Yes.
do you assume there exists such a Z? Do you only use it to define Z theta inverse?
Oh, right, so this is a function with, I don't know,
It's a normalizing.
nice properties so that you can actually take its inverse.
It's just a normalizing. It's just so
Yeah.
that the,
Yeah, it's
the
a
sum of
normalizing
the pj is
function.
equal to 1. So basically, it's the z theta is the sum of h, j,
Indeed.
and the product inside. It's just so that the pj's are the sum of the pj's equal 1.
Okay.
Yeah, it's just a normalization. Because the sum of all the PJs has to be 1. And if you just take that this, then in general you don't get that.
Because I mean, it's just a value, right? You don't need the entire function Z. You only.
I guess you only need, yeah, but we don't know what theta is. But so given theta, we would only need z of theta. So maybe yeah, maybe you don't need this whole function because we also already fix it here. So sure.
Just to check, in Amin's and my talks, or really in Amin's talk, h was a function and now it's a number. Does it matter? I mean, it can be viewed as a constant function, but like it was a function.
I guess I agree that h was a function, but I guess we just mean its value because it's a function with image in it, right? In it, I think also everywhere we will just so there was a bit about where we can reduce to h being constantly 1. And I think we'll do that throughout, and I've already done it here, for example.
It was a function from where to where?
From omega to the positive reals to the r. Omega being the implicit probability measurable space that it's kicking around. I think. Also, is it possible to close? Is it possible to close the blind? Because I think that at the moment the left board will be.
From here.
I think so, yes.
Yeah,
It's
it's
also-
hanging down there.
Oh yes. Let's see which one you are.
The one
No,
where
not that one. Good enough?
Maybe it has.
Yeah, okay.
Reasonable.
Okay, sure. Yeah,
Yeah,
just in this relevant part.
I think that in your statistical application, theta is going to be fixed but not known, and you're going to conditional
Right.
theta if I remember.
Right.
No, it's not conditional theta with
Sure, but I
traditional
mean,
sum.
it is fixed now, right? It is fixed now.
It is fixed,
But,
Yeah.
but
but we don't know what it is.
so the main problem that we will be testing is the hypothesis that P lies within, so this P that we have lies in this exponential family, and we will test that against the hypothesis that does not. So how would we do that? Well, we have to look at the p-value, or we can look at the p-value, maybe I should say, which is the expectation of the following quantity. I'll first write it down. And maybe you should write V there. Plus V with. So here we have an indicator function, which I'm sure everyone will be happy I wrote as a function. So what do we test? We test that right. So we rate it over all V's that have the correct number of draws. So we have some U that comes directly from our data, and we want to know how likely is it that this. We want to know something about all the outcomes that are less likely than that. So this is where the statistic T comes in, because in case for every V that does lie in the family, or weighted by n lies in the family, T equals 0, and otherwise it's bigger. So we want to. So this indicator function tests whether or not the V lies in that.
What is the domain of the function?
Of this indicator of this the.
Yep. What is V an element of?
So V is an element of.
It's possible that that counts.
Yeah.
Oh no. Sorry.
Yeah. Yeah. It is. It's all the possibilities for all the vector of counts,
Yeah.
given that we know that the total number of counts is n,
Well, that
which.
disagrees with your
Oh,
capital V definition, but
No, it's just from n to the r, right?
Yes,
Little
wait.
v.
yes.
Wait.
Because that's what you feed to the function
I messed
t.
up now. Hmm?
I think you don't
The
need capital
function t
V.
is defined from n to the r,
Yes.
so your v's live in n to the r.
Eric,
Yes.
I think, I'm not sure, that the sum of vi equal the sum of ui, just
Right. Yes.
it's not n, just the sum of ui.
You are correct. That is not n.
Yeah, but
Isn't the sum of ui?
Is that n?
some of you are amazing.
Is
Oh
n?
yeah, sorry.
Yes. I thought I knew this, but why is that n? Oh yes, because we.
We just
Oh,
count.
yeah.
Standard
Yeah.
outcomes.
Yeah, it's just,
So-
yes, yes, the sum of the, yes, so this is indeed what we need. But maybe this is indeed helpful, because, so we have n data points, and the U just collects them, just makes collection of their values. So we, so the sum of the UIs have to, every data point, every xi is somewhere between 1 and r, and all of them get counted. Right, so the sum of the UI has to be.
Yes, but there are two problems, and one is what is the expectation taken over, and do you
Yes,
really mean little
yes.
v?
So this,
And I think by little v you mean a big V, but not that one.
not that one.
No, because I think what you need is
Because I thought that's
the vector of counts thought of as a random variable. So
right.
you could define capital Vj,
Right. Yeah. So
is the
the
number of
author writes capital V here.
yeah, but then we need capital V to be defined properly,
Yes.
and I think it should be defined analogously to your definition of U,
Right.
which would be capital Vj is the number of I such that
Right,
capital Xi
right, yes.
equals j.
Yes. So yeah. Okay. So
It's the random number, the vector of random counts.
yes.
Yes,
But
this I would agree with, but that's not in the element of one dot 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 r to the end.
no, that's not.
But just forget that.
Yes. Okay. Right, but there's another problem, and I think maybe this is one of the things that you mentioned, but that was.
And the other problem is what expectation, what
Yes,
distribution
so-
is used.
so indeed, and I explicitly suppressed that to now tell you, oh, but actually we will need to know, if you want to calculate this expectation, you already have to know what P is. You can't calculate this directly, and this is the problem. So I'll call this equation, this value, star, we need to calculate it, but we can't. Now there are two ways out, at least the book handles two ways out. One is an asymptotic approach, but we'll skip that for today. And one of them is another approach, which we will.
Can I briefly say what the usual sort of conventional choice would be, or conventional definition of the p-value in this case?
Right.
So you would take the supremum of what you have written down
Okay.
over all p's in the hypothesis 0, h0.
Sure.
So it would be sort of the worst case, or best case. You actually observe the value t of u,
Yes.
and you ask yourself, is this compatible
Right.
with
So that would
the
be,
hypothesis?
that would be a third approach to
Yeah.
calculate it. Yes.
That would be a third, but unfeasible.
Yeah, because there
Between
are lots
alternatives.
of b's in there, and
Yeah.
you have to calculate that for all of them.
I'm sorry, so where does this function, this indicator function, where does it go from and to?
It goes from.
Because we're evaluating it as a random variable, so yeah.
So
It's a function of little v, and we're
Yes.
evaluating it at capital V.
it's a function of.
What little b is an element of?
So at least it's very easy to say where it
Just
goes
set up
to.
to n.
And so where
Positive
does,
determinant?
yes, it goes from
Yeah.
from there, I guess. But
Non-negative integers which add to n
which add to n, yes, indeed.
would be good enough.
So, I have another question. I have a hard time putting this T in the right place in my head. Will you, at some point that's convenient to you, explain in the teacup story what these things are?
I wasn't planning on doing that, but maybe we can do it together. So how does this relate to the teacup story?
Well, you can also save it for later if that's more convenient.
Yeah, I was going to draw one sort of parallel to the teacup story, but I didn't want to do it at every point, mostly because I didn't prepare that. I guess so far we're just sort of treating a general method that relates to that historical motivation. Right. Okay. So we're going to try and find a way around the fact that we can't actually calculate that. We're going to pretend that we can. We're going to we're going to calculate something else, and we're going to pretend that it's close enough to that value so that we can say something. So we will define a set which we will call f of u, and it will be those v's such that a v equals a u. And actually here you see a relation to the teacup story, because in the teacup story we can write it out in matrix A that calculate that's so what this says is that every v, so we're going to we're going to from now on assume that all the v's that we're looking at live in this fiber. So we're going to restrict ourselves to just that, to those v's. And what is the property of those v's? Well, they have something related, they have something fixed with respect to what we actually observe. And in the teacup story, that is, we know that we have 4 cups with the milk poured first and 4 cups with the tea poured first.
So I think in the teacup story is R equal to 4, and it's so the basic things are per teacup, whether the milk was poured in first or not, and
Right.
whether the lady said it was poured in first or not.
Right, okay,
Right.
yes, you need to compare those 2 things.
You compare those 2 things. You've got 8, so n equals 8.
So,
N equals 8, I think.
yes,
There are 8 teacups,
yes. And for every...
and each teacup we get to.
But I guess you can do with R equal to 2, because you just want to know milk first or tea first, right? That's just a...
Well, that's the truth, whether the milk or the tea was
Yes.
first, and that's what the lady said, whether the milk was first
Right.
or the tea was first. But which is, let's take it to be random.
Mhm.
But so each teacup gets classified in one of 4 ways.
Right, yes.
At least that's how I would.
Yeah, I
Do.
think that's a good way to do it. Mhm.
And then the A, and then the
The A will just...
the numbers of teacups of each kind,
Yes,
which are classified by the lady in each way.
yes.
That's the 4 numbers. And you're interested in the U's, so that which add up to 2 groups of 4,
Yes,
because she's so clever always to
to at least keep that in mind.
to use that.
To
in her
use the
decision
data that
making.
she's given. Yes.
That we can do.
So we decided that K is 8 and R is 4. Was that the conclusion?
That would be my
And-
suggestion. Yeah, would be one way to.
Okay.
N is 8. Oh, but was K, yeah. What was the question?
what is
it's 2, I think, because there are 2 constraints on these numbers.
Yes. Sure.
You're going to observe 8 numbers, and in 2 pairs they should add up to 4. I think.
Right, yes.
Or
Because-
possibly in 4 pairs.
So what's
Sorry,
K?
in 4 pairs they're going to add up to 4.
So what is K?
What was K?
So K is the number of rows of the matrix. So here's the number of, I would say that is the number of constraints, right?
So maybe we'd better have it equal to 4, because there are okay, each of 8 teacups can be classified in 2 ways. Both namely how they really were prepared and what the lady said. So that means each teacup is one of 4 kinds in our data. And we know that
So there's 2 sounds.
teacups initially were prepared with 4 with milk first and 4 with milk after. And we know that ladies said, specified a certain 4 to have milk first and a certain 4 to have milk after. So that is 2 linear constraints on those numbers. So R is 2.
Yeah.
K
K
is
is
2.
K is 2.
K is 2.
Sorry, R is 8. K is 2.
Yes.
And R is 4.
And then it's 8.
Can we just write down? I've really become lost now.
So in the
Eight
historical
cups of tea.
example,
Mm-hmm.
we had R equal to 4, M equal to 8, and K equal to 2.
But that 4 is not the 4 from the 4 cups.
No.
No, that is
Yeah.
2 times 2, because
Yeah.
that's the 2 possibilities times the 2 other 2 possibilities. The 2 possibilities of the guesser times the 2 possibilities of the truth.
So can we write down the matrix A, or do we need more information to do that? I think we should be able to.
We-
I think we could do it,
Yeah, we
but
could
I
do that.
but I want to do other things.
We just have to decide what is the order in which you
Yeah,
going to
that's it.
list those
Choose an order.
4 things.
Yes.
Okay.
And once you've done that, then you have got the matrix A is two rows consisting of zeros and ones, and each row
Well, I'm
has
still
got
confused.
two ones and
No, that's
six.
a good question.
Uh, no, sorry, yeah, two ones and two zeros. It says this number plus this number equals 4.
Yes, yes, because indeed.
I see.
So it's sort of, I mean, it's a
It's a 2x4 matrix?
2x4 matrix.
Yeah,
Yes.
it's got a 1, 1, 0, 0, 1, 0, 1, 0.
Awesome, thank you.
Once we've
If,
chosen
if you put these, those 4 things in
in the right
a
order.
suitable order.
So, just in the case of the historical motivation, we will now, from now on, we're going to restrict to this fiber. So we'll only test those fees that are in the fiber. Because like in the historical motivation, we might have some reason to assume that will be in there anyway. I mean, the lady won't say, oh, these 5 were prepared with milk port first, because she knows that that's not going to
She's
happen.
a really smart.
She's pretty smart. I mean, she's a scientist, right? So
Yeah. What's
She
she
is.
on
I think
mycologist?
mycologist, yes.
Mushrooms.
So if we,
And the P is going to be a P in the model in MAH,
yes,
and the model MAH with H equal to 1
1.
in this case. H is going to be 1. Says that the lady's choice of 4 is completely random.
Yes.
Right.
Because that's the sort of ground hypothesis. She can't, and only she has to
Oh,
pick
I see.
sufficiently cups correctly for us to believe that she actually can,
Yeah.
or she cannot not.
Now, T could be the number of correct choices.
Sorry.
T.
Oh yes, yes.
The statistic we're interested in, and we've got a U
No,
where
but maybe
T of U
we
equals
want T
8.
of the. We want T to be 0 for those.
If she does it completely random.
If she-
Oh, yeah, so I just think, okay, so think again about
Yeah.
it. Should be- We have to come up with some measure of how far her numbers are from what would appear to be from what we would expect
Yes.
under complete randomness.
Yes.
Under complete randomness, we would expect 2, 2, 2, 2.
Yeah.
Yeah. So you could take the squared Euclidean distance of her vector for
2, 2, 2.
numbers 2, 2, 2, 2, 2.
Yeah.
That would be a sensible thing to look at. And then you want to ask yourself, is what we've actually seen incredibly unlikely under this model?
So assuming that P is of the form that that's in H0, well, I just erased it, that wasn't very clever. The likelihood of U given theta is as follows. I will write first and then explain a bit. So this is all recognizable from the form that I just wrapped up, and this coefficient is defined as. This is the multinomial coefficient, and you have how many are? Okay, and so very clearly that depends on theta. But if we if we assume a bit more, namely we are in this fiber, we get some interesting property, namely the following lemma. Namely that this conditional likelihood, where we also assume we're in this fiber, is actually independent of theta. And the proof is actually quite short, because what would it be? Well, just a general this is that likelihood, and because we assume, so if for every W in the fiber, AW is the same as AU, and V was in that fiber, so that's also the same. AV is also the same as AU. So not only do these cancel, that's just it's completely that's always going to be the case, but also these will cancel out, and then you get something that's not at all dependent on theta.
And is the thing that you've written down the conditional likelihood?
Yes.
Okay. And is likelihood the same as probability?
Yes, from a different point of view. I mean, the likelihood is it has the same formula, but it's just an expression, a point of view of what's fixed and what's your variable.
I don't have that kind of point of view.
You don't have to, so
I'm a
you could
religious
just say probability.
You can
Okay.
just say, yeah. So, now, and by that I mean assuming that you only test the V's that are in the fiber, the quantity in star equals, or 1 over the number of elements in that fiber times the sum over the fiber
Yeah, and so your expectation right there with the star is the conditional expectation given the value of AV.
Yes, yes.
And
Because
the lemma says, and this no longer depends on P,
yes, indeed.
if P is in the model.
So we fix AV because U is given. We are given some data, and we can do data little x's, and we can just count. So U is part of our knowledge, and we can just so we know AV, and now we can just say, okay, we only take the V's. So we know AU, we can only take the V's fixed in such a.
So star is not equal to that, right? There's some restriction to the fibre, or have I misunderstood?
Right.
No, star should be rewritten. He's looking at the expectation for any P in the model of that indicator, conditional on
Maybe instead of equals, I should
T
say is replaced.
conditional on something equal to some value, conditional on the observed value of a v. Right, capital V is vector, A is a known matrix,
So,
and A.
so when
That would be
we,
good.
so we range,
A capital V is A small u.
we let the
Yeah.
expecting value range over some fees, but now we just restrict our range. And if, so if we already did that restriction there, then it would be the same. But
So this, whenever you say we restrict to only these V's, or we assume that we only look at these V's, is that the same as stating some conditional?
I think that what he's doing is stating a conditional probability, yes.
yes.
Okay.
I wouldn't say it using his words.
Okay.
So may I hear how you would say it?
I would say, star, we're going to look at the expectation of that indicator conditional on a
Yes.
Yeah.
matrix known fixed
Right.
times random vector capital V equals capital A little u.
Yeah.
So we condition on the actually observed value of a v, and the nice thing is that if the model of is true, is correct, the H0 model, which says basically she doesn't know what she's doing, but she could be choosing systems. No, I'm not quite sure. It depends what theta would be. So,
She doesn't know what she's doing except for
but
being
anyway,
smart
she,
enough
yes,
to,
what
Yes,
she's doing has got
indeed.
nothing to do with what's actually in the teacups,
except for
She
the
knows
fact that
there
she
are
knows that
except
there's
she
four.
can get the right number.
Yeah.
Then that conditional expectation does not depend anymore on P. Because she can be doing something which is random. So it can depend on some probabilities which we don't know.
I'm not sure I understand the last statement, but maybe we can.
Well, maybe she sort of systematically chooses cups 1, 2, 3, and 4, or something like that, or I don't know. Or randomly chooses the even numbered cups, or the uneven numbered cups, or something. And the theta would describe all the ways she could make her choice at random, but without knowing what's actually in the cups,
Yeah.
I think.
And so we call this quantity star prime, and I believe that what is called Fisher's exact test is calculating this, but
For a particular choice of T, you know.
yes,
particular
yeah, sure, because,
circumstance.
sure, because it depends on which T we choose. So maybe for every T there is a Fisher's exact test.
Fisher had a particular T in mind.
Okay.
Because this seems super sensitive to your choice
And
of
a
T, right?
particular situation in mind. So
Yes.
a particular.
I mean, this is a
Age.
this is a very strong generalization.
Because, I mean, can you like comfortably arrange to have any p value you want just by scaling your function t? It seems very heavily dependent on t.
Yeah.
Okay, that seems a
So
downside.
so the rule book is that before you do the experiment, you say what T you're going to use.
Okay.
And this is the rule in the rule book which is broken most often in applied research.
Sounds very tempting to break it. So.
Yes, it is very tempting to break, yes. Especially if your research costs a lot of money and it's got to be finished at a certain time and please certain people.
So now from a theoretical point of view, we're done, we can just say, okay, we can calculate this. But actually, from a practical point of view, we have a new problem, mainly that f of u could be very big, or it could be difficult to calculate. Or, I don't know, something, I mean, this expression we might have no actual way to handle it. So the proposed solution is to generate samples of f of u. So something maybe I should mention here. So this distribution. So yes. So after we've cancelled the thetas, we may recognize a probability distribution which takes this form, where this just means there is a linear factor that I've suppressed, and this is called generalized geometric distribution, and this is just this is a known distribution, and we can sample from that. So we generate samples of that with respect to the generalized hypergeometric distribution.
Sorry, a silly question, but f of u doesn't look very hard to calculate. Like, it's just like linear algebra, right?
Yes.
Well,
Unless things are very
true, right?
But it might be.
It's a polytope thing, right? Integer points in a polytope.
Yeah, so the problem is indeed that we work over integers and not over q or
Oh, natural numbers.
natural numbers.
Otherwise it would
Yes,
be-
natural numbers.
Yes,
So
it's a combinatorial problem.
It is a
The problem
combinatorial
is
problem.
that if A is big and complicated, it can be very big.
So I guess today we're doing 3 subjects. We do probability, we do 4. Probability, we do statistics, we do algebra, and we do combinatorics. But the proposed solution gets around the combinatorics.
It's a bit strange, right? Because I think exactly in toric geometry, people try to do these things. To give
Yes.
formulas, to... Right?
Yes.
Yeah.
And it's no surprise that the results of today relate this sampling problem to this ideal I sub A, which is a toric value.
Yeah, the problem is, I'm sure it's not difficult to say how many elements there are in this set. What was it called?
F of fiber.
F of U, in the fiber. Probably you can find nice formulas for that. And the problem is you want to know how many of them satisfy a certain constraint T of something is bigger than something else. And
Which means not
that
linear.
functional T will typically be quadratic or have logarithms or
Okay.
will be something
Okay.
complicated.
Yeah.
Certainly not linear.
Okay.
So even if we can calculate all the points, then still that sum might be very difficult.
Yeah, we can easily see if a point is in there or not, and probably we can count say what the total number is, but the number which satisfies this
Okay.
condition indicator, that will be
Yeah.
not feasible.
So how will we go about generating these samples? For that, I first introduce a definition that we won't use immediately, but well, I want to write it down. So we keep A as such, and So remember, we will use the notation kernel of A to be those vectors in Z to the R such that A equals 0, naturally. But the definition is as follows: a finite set B in this kernel is called a Markov basis for A. If for all u in to the R and u prime in its primer, there exists some v1 up to vl in plus or minus b, satisfying two things. One,